I'm Frank Wilczek. I'm a theoretical physicist, but I aspire to know about everything in the world, to be a good person and to make it a better place. Our present understanding of the fundamental nature of matter is unusual but profoundly simple. We think that matter is made out of a few kinds of building blocks, which are usually called fundamental particles. For ordinary matter, you can count the significant building blocks really on the fingers of one hand and have some to spare. So there are quarks, gluons, photons, electrons, that's it. Okay, if you want to be a fuss budget, you could say that there are two relevant kinds of quarks, up and down quarks. So now I've used 5 exactly. If you want to do justice to cosmic phenomena, you should also introduce gravitons and neutrinos. It's still a very finite number of building blocks. So two new forces were introduced, at first just in order to account for experimental phenomena. One is called the strong force, and that's responsible for holding the nuclei together. And then at a deeper level, we learned it's responsible for making protons out of quarks and gluons, which are the simple building blocks. And then the weak force, which is responsible for radioactivity and other forms of chemical change, but is a much weaker force, as its name portends. And that's it. So the important thing is that that's it. It's a very finite list. And one big enterprise in physics is to try to make the list smaller in some sense, conceptually smaller. And we're not going to get rid of those particles, they really exist. But maybe we can relate them to each other and get a more unified description. And similarly, the forces, maybe we can see them all as aspects of one force that manifests itself in different ways, but are conceptually unified. The takeaway messages are that there are a finite number of building blocks, a small number of interactions, that they're mathematical, that they're local, and that they describe, as far as we can tell, all the phenomena of matter in principle. People have done very, very demanding experiments in extreme conditions at accelerators, measured things very, very accurately. But so far, this understanding of nature has really held up very, very well in its modern form since the mid-1970s. It really hasn't needed significant change at all.